Good evening, everyone. So welcome to my channel, YouTube channel, Maths Avatarm. Today we are going to start new topic. So this is lecture 1 on functions of bounded variation. Okay, it's very interesting topic. Still, if you have not subscribed my YouTube channel, subscribe it for such type of interesting topics. Okay, so let's start today's session now. Okay. So before starting topic, functions of bounded variation. So we have to attend one or two things. Okay. First of all, let A, B belongs to R. Okay. And B closed interval. Okay. So it means I am taking closed and bounded interval. Okay. Okay. A set B of finite numbers of points x0, x1, x2 up to xn such that A naught is equal to x naught is equal to A and x1 is strictly greater than x0, x2 is strictly greater than x1 and x3 is strictly greater than x2. Okay. And this is xn minus 1 here will be somewhere here. On this is on large xn is equal to B. Okay. Is called partition of closed interval A. Okay. So now you see that there are infinitely many partitions of B. Because I have n number of points, I can increase points. Okay. I can decrease the distance between 2 points. Okay. So there are infinitely numbers of partitions of closed interval AB. Okay. So I write row AB means P such that P is partition of closed interval AB. I am collecting all the partitions of closed interval AB. Okay. Let's give some bracket. Okay here. Okay. Okay. So consider corresponding to the partition P, we write SP. SP means what? I am taking SP. So SP depends on interval, partition P. Suppose P have finite numbers of points n. Then I am writing this. Sorry. I will write this later. Okay. So I have to write one here. Let f be a function defined on closed interval AB. Okay. Okay. Given a partition P, partition P of closed interval AB, we write what we write? SP is equal to summation I goes to 1 to N F X I, so I goes to 0 to N. Okay. 0 to N. Fi plus 1 minus Fxi. Okay. I goes to from 0 to N. So obviously note that SP is greater than equal to 0 for any partition P. Partition belongs to this because we are saying that collection of all the partition this row AB. Okay. What is the definition of function of bounded variation? Definition. So I am taking, let AB belongs to R such that A is still less than B. Okay. Then a function f from closed interval AB to R is said to be a function of bounded variation okay, if supremum over intervals, sorry, partitions okay exists. Okay, it means if supremum SP exists, you are taking this supremum over P, partitions of AB. Collection of all the partition is denoted by row AB. If this supremum it exists over row AB, you are taking P from this row AB because P is partition, and you are taking supremum. Okay, then the function f defined on closed interval AB is said to be function of bounded variation. Okay. If f is function of bounded variation, okay, defined on AB, then we write, okay, V means variation, F AB, okay, that is supremum SP, okay. and call SP call the total, we call this the total variation of F, okay, and we call this total variation of F, okay. This is BFAB, that is supremum over ST, because F is function of bounded variation. This exists, it exists means it is finite, and we call this BFAB the total variation of F, okay. Okay. So we have flowing observation. Okay. Flowing observation. Observation first. Okay. Let F A B to R. Okay. Be defined. Be a function. Okay. Then for any partition P, we have F B minus F A is less than equal to SP. Okay. Let's see its proof. Suppose I am taking a P which has only 1 point. Okay. 1 point. That X0 is A and C is somewhere. X1 is somewhere and X2 is B. Okay. I am treating this case first. Okay. Now FB minus FP. I can add and subtract. So this implies FB minus FX1 minus FA plus FB minus FX1. So it means FB minus FA less than FB. Now I have checked if P has 3 points. If P has more than 3 points, still we can add and subtract. Okay. So if partition increases, the number of partition increases, then SP always increase. Okay. Okay. So if B has more than 3 points, Using the same technique, we have, because I have checked for 3. If it has a 4 points, okay, if it has a 4 points, then still using this technique, you can prove it, okay. We have FB minus FP, okay. So SP, okay. So this is so, okay. Now, observation 2. Observation 2. If P1 partition is subset of P2, then SP1 is less than equal to SP2. Okay. Okay. Let's see its proof also. Suppose P is this, P1 is this, A naught is equal to X1, X1, X2. And somewhere I am taking C point here. Okay. Some X, L is here. Okay. Sorry. Suppose X, okay, L minus 1, XL, XN. Okay. Suppose, and let P is contain at only one more point. P2 contain only one more point. Okay. In this case, P1 is subset of P2. Okay. P1 is subset of P2. So what we have? So what is SP1? SP1 is F Xn minus F Xn minus 1. Okay. That is first point. Fx2 minus Fx1. Okay. Fx2 minus, sorry, Fx3 minus Fx2. Okay. This is Fxl minus Fxl minus 1. And so on. Fxn minus Fxn minus 1. Okay. Now, in this point, because my P2 has only one point, P2 has only one more point, I will add and subtract FC minus FC plus FC. Okay. So I am adding here. So I will keep these points as these things as well. I will add here FC and subtract fxn minus fxn minus 1. Okay. This is equal to this. Now I can use triangle inequality here. Then this summation will be increased after applying triangle inequality. So fx2 minus fx1 plus fx3 minus fx2, okay, plus fxl minus fxc plus fc minus fxl minus 1, okay, fxn minus fxn minus 1, okay. So this is, what is this? This is nothing but SP. So this implies SP1 less than equal to SP2. Okay. Okay. Now I have taken P2 which contain only one more point. Now suppose P1 is subset of P2. P2 contain more some n more points. So you can select P3 which contain more than 1 point than P2. Okay. Okay. Now we are taking general case. Okay. Let P2 contains m more points than P1. Then there exists sequence. Okay, there exists sequence. Choose m belongs to row A, B, sequence of partition, or m is equal to 1. Sorry. K. For K is equal to K is equal to 1, 2, 3 up to m. Okay. Such that P1 is contained in Q1, Q1 is contained Q2, like that QM and that is P2. Okay. Having the properties okay. Q1 contains one more point than P1. Okay. Then P1. Okay. Okay. And 2k minus 1. k plus 1 contains one more point than q for k goes to 1, 2 up to m minus 1. Okay. M minus 1. Okay. Q2 contains one more point than Qm. Okay. Now let's say this equation number 1 by equation 1 we have, because SQ1 will be less than SQ1 because Q1 contains one more point than P. Now Q2 partition contain more than one more point than Q1, so it will be less. So continuing in this way, this will be SQM and last one will be SP2. Okay. So this implies SP1 is less than SP2. Okay. So result is true. Okay. Now observation 3. If F A B to R be a function of bounded variation, then S FB minus FA is less than okay. Yes. Let's see it's true. By observation 1 we have FB minus FA is less than SP for any P belongs to row A, B. Okay. Okay. Taking supremum over P belongs to row AB, we have FB minus FA supremum P belongs to row AB SP. Okay. Because function is bounded variation, so it will exist. So it will exist and it will be finite. Supremum will be finite because it is function of bounded variation. And what is this? This is equal to okay. So this implies FB minus FA will be okay. Next observation 4. Every function of bounded variation is bounded. Okay. Let's see its proof. Let f a b to r be a function of bounded variation. Okay. Bounded variation. Okay. Then what does it mean? Then VFAB is finite because function is bounded variation. Supremum P belongs to row AB. SP exists, that is BFAB, that is finite. Okay. So I am writing in expanded form. BFAB supremum P belongs to row AB. SP is finite. Okay. Because function is bounded variation. Now let X belongs to closed interval AB and consider the partition P is equal to A X. Okay. B. Okay. Okay. So I am taking let I am taking A in between. Okay. Now 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 from observation third, we have what we have. Sorry, not by observation. This is not by observation. Now you see that SP is less than supremum P belongs to row A, B, SP. That is, okay. What is this? This is nothing but because F X minus FA plus FB minus FX. Okay. SP is this. So this will be less than VFAB. Okay. So what is this? So this implies Fx minus Fa. Okay. Is less than Fx because they are non-negative quantity. B minus fx that is less than BFAB. So this implies fx minus fa is less than FAB. Okay. So this implies now what is fx? Fx is I can add fa and subtract. So this is less than okay. So this implies this is what is this? This is BFAB less than this is less than BFAB. So I'm writing here. Okay. So this implies fx is less than BFAB plus FA. Okay. And now if I put, because x is in between A and B, so it is satisfied. If I am taking A here, this still, because now if x is equal to A, then this is true for 0 to, A x less than B. If I am taking x is equal to B, then FA is also less than FAB. So this inequality will work here. Okay. But what about x is equal to B? Then I want to make it. So then what I will do? It will not work. It will not work. Okay. So for x is equal to B, it will not work. So I want to make it some inequality, more inequality. Okay. Okay. So take m is equal to BFAB plus FA plus FB. Now see that FB, mod FB will also less than equal to m. Then for any x belongs to closed interval AB, we have fx less than m. This implies f is bounded. Okay. So every function of bounded variation is bounded. Okay. Okay. So we have proved that every function of bounded variation is bounded. So today's lecture up to this. So thank you very much for today's lecture. If you have any problem or issue related to this lecture, you can comment me on my YouTube channel. Okay, I will take care and I will discuss you in next session. So thank you very much for today's lecture. Thank you very much.